Hello everyone and welcome back. We have been exploring eigenvalues and eigenvectors, and today we are going to tackle a slightly more advanced topic, complex eigenvalues. Sometimes when we solve the characteristic equation, we end up with complex solution. Let's see how that works. As a quick refresher, eigenvalues are those values lambda which satisfy the equation a times v is equal to lambda times v. Here lambda is the eigenvalue and v is the corresponding eigenvector. We find eigenvalues by solving the characteristic equation, which is given by determinant of A minus lambda I is equal to 0. So far, we have dealt with real eigenvalues, but what happens when the characteristic equation gives us complex roots? Let's take an example. Consider the given matrix. We will be finding its eigenvalues and also the corresponding eigenvectors. To find the eigenvalues, we will start with solving the characteristic equation, which is given by determinant of A minus lambda I is equal to 0. And in this case, we get determinant of negative lambda, negative 1, 1 and negative lambda is equal to 0. Therefore, we get lambda squared plus 1 is equal to 0. And we know that the roots of these equation are lambda 1 is equal to I and lambda 2 is equal to negative I, which are complex in nature. Now we will be finding the eigenvectors corresponding to both lambda 1 and lambda 2. Consider for lambda 1 equal to I. We begin by solving the equation A minus lambda I times V is equal to 0. Here we are going to plug in lambda 1 as I. So we get A minus I times I into V is equal to 0. And from our given matrix, we have negative I, negative 1, 1 and negative I. We will be expressing it as column vector x1, x2 and 0 will be expressing it as column vector 0, 0. On R2, we perform now. R2 changes to R2 minus I times R1. Let us see how that affects the R2 elements. For this entry, we will have 1 minus I times of minus I, which gives us 1 plus I square, and that is 0. So here we have the first row remaining unaffected. In the first entry in the second row is 0. Now let's work with the next entry, which is negative I. So again performing the ERO gives us minus I times of R1, which is minus 1. And this gives us minus I plus I, again which is 0. So thus this entry is also 0. And we have x1, x2 is equal to column 0, 0. So therefore we get minus I times x1 minus x2 is equal to 0, or I times x1 plus x2 is equal to 0, and therefore we get x2 is equal to minus I times x1. So therefore the eigenvector v1 is equal to x1 comma minus I times x1, where x1 is a real number. If we put x1 as 1, we get v1 is equal to 1 comma minus I. So this is the first eigenvector corresponding to lambda 1 equal to I. Now let us check for lambda 2 equal to negative I. Again we begin with the equation A minus lambda I times V is equal to 0. That is A plus I times of I into V is equal to 0. So here we have I minus 1, 1 and I multiplied by V, which is x1, x2 is equal to 0, 0. On R2, we now perform R2 changes to R2 plus I times of R1. So the first row remains unaffected and the right hand side remains unaffected. Now let's focus on this entry. So we'll be performing R2 plus I times of R1. The R1 entry is I. So we get 1 plus I square. That's 1 plus minus 1, which is 0. So this entry is 0. Now focusing on the next entry, we have here I in R2. So we get I plus I times of R1, which is negative 1. So this is going to be I minus I, and again that is 0. So we here get 0, and simplifying we end up with I times of x1 minus x2 is equal to 0. So therefore we get x2 is equal to I times of x1. Therefore the eigenvector v2 is going to be x1 comma ix1, where x1 is a real number. And again if we put x1 is equal to 1, we get v2 is equal to 1 comma I. Now make the following observation. When lambda 1 was I, we got v1 as x1 comma minus I times of x1. When lambda 2 is equal to minus I, we got v2 as x1 comma ix1. When we have complex eigenvalues, the corresponding eigenvectors are also complex. Also, the eigenvectors are complex conjugate of each other's. Complex eigenvalues and eigenvectors might seem a bit daunting at first, but they are just another tool in our linear algebra toolbox. Remember that the process is the same as with real eigenvalues. The only difference is that we are dealing with complex number. If you found this video helpful, please give it a thumbs up and subscribe for more linear algebra tutorials. Let me know in the comments if you have any questions or suggestions for future videos. Thanks for watching and happy learning.